Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss one-dimensional linear harmonic oscillator in quantum mechanics. Means we have to study about the eigenvalues, eigenfunctions and uncertainty relation in linear harmonic oscillator, which is known as LHO in quantum mechanics. Let's begin. What is a linear harmonic oscillator? A linear harmonic oscillator is a point particle that is attracted towards the center by a force, and that force is proportional to the displacement from the fixed center. If I draw the graph in between potential and displacement, this is displacement axis, that is potential axis, then the graph is looking like this, just like a parabola. Means at mean position the potential will be minimum, and after some displacement gradually the potential increases and so on. This is a typical linear harmonic oscillator. We know in classical theory of linear harmonic oscillator, the force which is directly proportional to that of displacement. That's why the force F is written as a proportionality constant, let K, which is known as the force constant or spring constant, and displacement x. This is the force. And the potential energy, the function for that of potential energy U of x, that is half kx square, that is half m omega square x square. And that potential energy function is symmetric. Symmetric in the sense u of minus x is equal to u of plus x. The Hamiltonian of the oscillating particle, the Hamiltonian means the total energy. Hamiltonian of that of oscillating particle, that is the kinetic energy plus potential energy. Kinetic energy is p cap square divided by 2m plus potential energy u of x, that is p cap square 2m ux half m omega square x square. Since the potential is symmetric, therefore the Hamiltonian should be symmetric, means h cap of minus x is same as h cap of plus x. Now we introduce the time independent Schrodinger equation. What should be the form of that time independent Schrodinger equation? So take a look here. The time independent Schrodinger equation, if we consider the wave function as psi, what happened? D square psi dx square plus 2m by h cross square e minus potential term half m omega square x square of psi is equal to 0, or separating these two terms as multiplied that factor d square psi dx square plus 2me divided by h cross square minus m square omega square x square divided by h cross square of psi is equal to 0. For simplifying the term, let we introduce y is equal to under root of m omega by h cross into x. Therefore, or x will be h cross by m omega square root into y, whereas y is the displacement term. So, therefore, d psi by dx, we use the chain rule here, d psi dy into dy by dx, we use just chain rule, is equal to d psi by dy, d psi by dy, then dy by dx, we differentiate y with respect to x, we have only that constant term, so that is m omega by h cross square root. This is for d psi by dx. Again we differentiate that psi with respect to x, what we have? Again we differentiate, therefore d square psi by dx square is equal to, that is d square psi by dy square into dy by dx. As we differentiate once time that term, that means d by dx of d psi by dx, here d by dx of d psi by dy, there will be d square psi by dy square into dy by dx, just a chain rule, and that constant term m omega by h cross square root. Again simplifying that one, d square psi dx square is equal to that is d square psi by dy square, d square psi dy square, again dy by dx as the square root of m omega by h cross, so the square root of m omega by h cross into the square root of m omega by h cross, that means the square root of m omega by h cross, we have m omega by h cross only. We have d psi by dx and d square psi by dx square. Now implement these two terms here. This is the substitution. Now we write here, that is m omega by h cross, d square psi dx square plus 2me divided by h cross square minus m omega square divided by h cross square, h cross divided by m omega y square of psi is equal to 0, or m omega by h cross d square psi d sorry, d square psi by dx square, d square psi by dx square, here will be d square psi by dy square, same d square psi by dy square, plus m omega by h cross 2e h cross omega minus y square psi is equal to 0, or d square psi by dy square, d square psi by dy square plus 2e by h cross omega minus y square psi is equal to 0. Since taking as common m omega by h cross, that term will not be 0, m omega by h cross not equal to 0, or d square psi dy square plus lambda minus y square of psi is equal to 0, where lambda is equal to 2e divided by h cross omega. What we introduce here, before getting the complete solution, we can analyze the behavior of that of asymptotic region, means the magnitude of y tends to infinity. As y tends to infinity, y square very greater than that of lambda. So that equation can be changed to a new form, d square psi infinity dy square minus y square psi infinity is equal to 0, and let that solution, its solution will be in the form psi at infinity of y is equal to e to the power beta y square, and d psi by dy, d psi infinity at dy, since that the solution will be e to the power beta y square, we have 2 beta y e to the power beta y square, and its square d square psi at infinity dy square is equal to 4 beta square y square e to the power beta y square plus 2 beta e to the power beta y square. Therefore, e 2 beta e to the power beta y square term as neglected, since magnitude of y tends to infinity, as y tends to infinity and y square is very greater than lambda. So that term d square psi at infinity dy square is nearly equal to 4 beta square y square e to the power beta y square. Okay. Or 4 beta square y square 4 beta square y square. No, here look at term here. Just we can do what is that term, d square psi at infinity by dy square is equal to taking e to the power y square just use these values in that of equation. Okay, just put the value of d square psi infinity by dy square, that is 4 beta square y square e to the power beta y square plus 2 beta e to the power beta y square, then minus y square y infinity, that is e to the power beta y square is equal to 0, which implies 4 beta square minus 1 taking as common y square e to the power beta y square is equal to 0, which implies that term treat as 0. Therefore 4 beta square 1 by 4, therefore beta square or beta is equal to plus minus half, beta is equal to plus minus half. So psi at infinity of y is equal e to the power plus minus half y square, as psi at infinity of y tends to 0 for y tends to infinity, hence the positive term means e to the power half y square, that is the positive term, is not accepted, is not acceptable due to the diverging nature, due to the diverging nature. So general acceptance is the negative one. Psi at y is equal to h of y e to the power minus y square by 2, that is the general acceptance, this solution, and where h of y is to be determined and h of y does not affect the asymptotic behavior of that of psi of y. Now change the variable psi y to hy. How to change that variable? Let us change that variable. D psi by dy is equal to dh by dy e to the power minus y square by 2 minus h y e to the power minus y square by 2. Differentiating that psi of y with respect to y, here first term treat as constant, derivative of second one, and again second one treat as constant and derivative of first one, that is the term. Taking as common dh dy minus h into y e to the power minus y square by 2 d psi by dy. Again second order differentiation, d square psi by dy square is equal to, again treating this as first term, that one as second term, derivative of first term second term as constant, and derivative of second term first term treated as constant. D square h dy square minus dh dy y minus h. Inside that a bracket hy, also derivative of first term second term as constant, again derivative of second term and first term treated as constant in case of hy, e to the power minus y square by 2 minus y dh by dy minus hy e to the power minus y square by 2 is equal to d square h dy square minus 2y dh by dy plus h y square minus 1 e to the power minus y square by 2. D square psi by dy square will be 0. Using that condition, so using the equation we have look here how to use this, may be taken as equation number 1. So d square psi by dy square will be minus of lambda minus y square of y. So using that equation here we can use using equation 1, using equation 1 we get in place of d square psi by dy square we use minus lambda minus y square of psi minus lambda minus y square of psi. The value of psi that is h e to the power minus y square, h e to the power minus y square by 2 is equal to as usual term d square h dy square minus 2y dh by dy plus h y square minus 1 e to the power minus y square by 2, or d square h dy square minus 2y dh by dy plus lambda plus h y square minus 1 plus h lambda minus y square e to the power minus y square by 2 is equal to 0, or d square h by dy square minus 2y dh by dy plus lambda minus 1 of h is equal to 0. Equation number 2. That type of differential equation is the Hermite differential equation. This is the Hermite differential equation. And its solution is in the form of power series. That is, solution is h of y is equal to summation over L from 0 to infinity a L y to the power L, that is the power series solution. So ds by dy is equal to summation over L from 0 to infinity a L times of y to the power L minus 1. Now dy dh by dy is equal to summation over L from 0 to infinity 2L into AL y to the power L, and its second order differentiation d square h by dy square is equal to summation over L from 0 to infinity L whole into L minus 1 AL y to the power L minus 2. Let us using this substitution in equation number 2. Using in equation 2, what we have, putting these values here, equation 2, that is summation over L from 0 to infinity AL L into L minus 1 y to the power L minus 2 minus summation from L is equal to 0 to infinity 2L AL y to the power L plus lambda minus 1 summation over L from 0 to infinity AL y to the power L is equal to 0. Just putting these values in that of differential equation. Now we have to substitute, or putting what? Putting L is equal to S plus 2 in first term, and S is equal to L in second and third. L is equal to S plus 2 and S is equal to L. Substituting here, and the summation from S is equal to 0 to infinity A S plus 2 S plus 1 S plus 2 y to the power S plus summation over S from 0 to infinity minus 2s plus lambda minus 1 as y to the power s is equal to 0. which implies summation from s is equal to 0 to infinity s plus 1 s plus 2 a s plus 2 minus 2s plus 1 minus lambda of as y to the power s is equal to 0. Since the coefficient of y must vanish, since the coefficient of y must vanish, so what we have s plus 1 s plus 2 is equal to 2s plus 1 minus lambda, sorry, that is a of s plus 2, a of s plus 2, here a of s. So a of s plus 2, a s plus 2 is equal to 2s plus 1 minus lambda divided by s plus 1 s plus 2 a of s. That is the recurrence formula. The recurrence formula. For large value of s, the function hy behaves as e to the power y square. As we implement hy psi y is equal to hy into e to the power y square divided by 2. But for large value of s, the function hy behaves as just like e to the power y square. Now as hy must terminate after a finite number of terms, that is hy reduced to Hermite polynomials are that of nth term. What happened are that of nth term? Here a of s, a of n is not equal to 0, but a n plus 2 is equal to 0 and a n plus 4 is equal to 0, etc. Therefore, a s plus 2 is equal to 0. That is 0 is equal to 2s plus 1 minus lambda divided by s plus 1 s plus 2 as, sorry, that is the value of a n, s as n. Just let us put in place of s as n, that is 2n plus 1 minus lambda divided by n plus 1 n plus 2 as a n. So lambda is equal to 2n plus 1. Or lambda is equal to 2e divided by h cross omega is equal to 2n plus 1, that is e nth term, or e n is equal to 2n plus 1 whole into h cross omega by 2. E n, that is the energy term, is equal to 2n plus 1 h cross omega by 2. The energy eigenvalues are given as the energy eigenvalues are given as for n is equal to 0, what happen? E0 is equal to h cross omega by 2, and for n is equal to 1, E1 is equal to 3 by 2 h cross omega. For n is equal to 2, E2 is equal to 5 by 2 h cross omega. Just we plot in a graphical view as this is the graphical representation that we prefer. That for n is equal to 1, sorry, n is equal to 0, 1 and 2. For 0 it will be h cross omega by 2, n is equal to 1 it will be 3 by 2 h cross omega, it will be 5 by 2 h cross omega. This is the graph of E. This is the plot of energy values. Look here, the energy of spectrum are equispaced, and the ground state energy, that is E0 is equal to h cross omega, is known as the 0 point energy. The ground state energy means E0 is equal to h cross omega, which is known as the 0 point energy. Okay, let us take the eigenfunction are obtained by using lambda is equal to 2n plus 1. Here we take lambda is equal to 2n plus 1, so the eigenfunctions are obtained. Put lambda is equal to 2n plus 1 here, that is d square hn dy square minus 2y dhn dy plus 2n hn is equal to 0, and the Rodriguez formula of that of Hamiltonian. The Rodriguez formula hn of y is equal to minus 1 to the power n e to the power y square, nth are the differentiation of e to the power minus y square, and the orthonormality condition, integration from minus infinity to plus infinity, hmy e to the power minus y square dy is equal to 2 to the power n factorial delta mn. So psi n of y is equal to an hn of y into e to the power minus y square by 2. As we introduce, this one is the acceptable solution, and an hn of y let me introduce in place of y, as we take y is equal to m omega by h cross square root into x, which implies y is equal to, that is a constant, alpha x. So in place of y we substitute what? Alpha into x, and e to the power minus alpha square x square by 2. Here alpha is equal to under root of m omega by h cross. Now using that of normalized condition, normalization condition, integration from minus infinity to plus infinity, psi n star x psi n of x dx is equal to 1, which implies magnitude of a square integration from minus infinity to plus infinity. An as treated as magnitude of a n square, that is hn star x alpha x and hn of alpha x e to the power minus alpha square x square dx is equal to 1, which implies an magnitude square integration from minus infinity to plus infinity hn star y hn y e to the power minus y square. In place of dx we substitute dy by alpha is equal to 1, which implies an magnitude square divided by alpha using that of normalized condition here, that is root phi 2 to the power n factorial is equal to 1, which implies n is equal to alpha divided by 2 to the power under root pi 2 to the power n factorial to the power half, and the wave function psi n of x is equal to alpha divided by 2 to the power n factorial root phi to the power half into hn of alpha x e to the power minus alpha square x square divided by 2. This is an and this is sine of x. Using n is equal to 0, 1, 2, 3 that of, so the Hermite polynomials are h0y is equal to 1, h1y is equal to 2y, h2y 4y square minus 2, h3y 8y cube minus 12y. So the eigenfunctions are psi 0x is equal to a naught e to the power minus alpha square x square divided by 2, and its graphical representation, first we write the wave function, then its graphical representations. Then psi 1 of x, that is a1, here 2x e to the power minus alpha square x square by 2, and psi 2 of x, a2 4 alpha square x square minus 2 e to the power minus alpha square x square by 2, again psi 3 of x, a3 8 alpha cube x cube minus 12 alpha x e to the power minus alpha square x square by 2. So psi naught x graphical representation as x and psi naught x graphical representation will be this. Again this is for psi naught x. Again psi 1 x, here psi 1 x this is second one. Then for psi to x, this is for what? Psi to x. This is for psi to x. Then for psi 3x, psi 3x. This is psi 4x. This is graph for psi not x, psi 1x, psi 2x, psi 3x. Now the probability density of that of nth eigenstates. What will be the probability density? The probability density in nth energy state, that is delta of x is equal to psi n of x sin star of x for n is equal to 0. For n is equal to 0, that is rho naught of x is equal to psi naught of x magnitude square, that is a naught magnitude square e to the power minus alpha square x square is equal to alpha divided by under root pi, and its graphical representation looking like this. If we take it as minus a, that is as plus a, and this stands for what? Rho naught x. This is the probability of finding that particle of that of region. Now the probability density graph represented by the probability density. How to get that of probability density? For that of corresponding wave functions, we have to take the probability density. First we take the plot of wave function and different different states. First view as this is psi of x, this is at x is equal to 0, and here the x axis. First n is equal to 0, here n is equal to 0. The wave function represented as what is psi 0 of x? This. So we relate that wave function as then the wave function n is equal to 1, it will be psi 1. For n is equal to 2, it will be, this is the psi 2. Then for n is equal to 3, this is the psi 3. And its corresponding the probability density graph. Probability density term is as shown, x is equal to 0, n is equal to 0, its corresponding probability density finding that particle in that region will be n is equal to 1, n is equal to 2, then for n is equal to 4, n is equal to 4, this is as n is equal to 4. This is the probability density, that means the finding that particle in that of given region. These are the graphical representation for that of linear harmonic oscillator in quantum mechanics. Now you have to take a uncertainty relation in case of linear harmonic oscillator. What is that of uncertainty relation? Uncertainty relation and linear harmonic oscillator. Uncertainty relation and linear harmonic oscillator. Assuming the uncertainty in the position of oscillator to be order of its amplitude and uncertainty in momentum to be the fluctuation in the value of its momentum between the limiting values. As the limiting value of the displacement, the total energy A is equal to, that stands for the potential energy and the kinetic energy, and it will be 0. But the energy of oscillator in the nth quantum state, the energy of oscillator in the nth quantum state will be 2n plus 1 h cross omega by 2. At due to extreme position, extreme in the sense x is at xn, at extreme position, at extreme position x is at x naught, where the kinetic energy is equal to 0 and the total energy is due to that of potential energy, okay, where the kinetic energy is equal to 0 and the total energy is stands for that of potential energy. Let me assume that potential energy be V. There will be, we write here, and the energy of that of nth state due to that of potential energy V half m omega square x n square. Now substituting this in En is equal to this much. Therefore, the value of En will be substituted here, 2n plus 1 h cross omega by 2 half m omega square xn square, or xn square is equal to 2n plus 1 h cross divided by m omega. Now the mean square displacement, this is the displacement term, the mean squared displacement, mean squared displacement, that is x square is equal to xn square divided by 2, that means 2n plus 1 h cross 2m omega. And the uncertainty in displacement, the uncertainty uncertainty in displacement. Del x is equal to, that is expectation of that of x square minus x square expectation square root is equal to 2n plus 1 h cross divided by 2m omega minus 0. Del x is equal to 2n plus 1 h cross by 2m omega square root. This is the value of uncertainty in position. Let equation number 1. Next we have to calculate the uncertainty in momentum. So the maximum kinetic energy of that of oscillator, the maximum kinetic energy of that oscillator, that is T max square, maximum kinetic energy, that is P max square divided by 2m, which is same as that of energy of nth eigenstate 2n plus 1 h cross omega by 2, which implies P max square is equal to 2n plus 1 h cross m omega. And the mean squared momentum, the mean squared momentum, that is p square expectation will be p square max divided by 2, that is 2n plus 1 h cross m omega divided by 2. The mean squared deviation in momentum, the mean squared deviation in momentum is, it is del px square, it is p square expectation minus p expectation square 2n plus 1 h cross m omega divided by 2 minus 0. So del px is equal to under root of 2n plus 1 h cross m omega by 2, equation number 2. That is the uncertainty in position, means the displacement, the position. That one is the uncertainty in momentum. Now multiplying these two, multiplying 1 and 2, therefore the value of del x into del px is equal to 2n plus 1 h cross by 2 for ground state. For ground state n is equal to 0 and del x del px is equal to h cross by 2. What is that one? That is the Heisenberg's uncertainty principle. That is the Heisenberg's uncertainty principle. And the Heisenberg's uncertainty principle, the product of uncertainty in position and uncertainty of in momentum is equal to h cross by 2. This is the uncertainty relation on linear harmonic oscillator. So with the help of this video lecture we understand the one dimensional linear harmonic oscillator in quantum mechanics. The solution of that form is accepted, but solution of that form is not accepted. Why? As we discussed. So using that form we take dy by dy which is the Hormone differential equation, and its solution by using power series method. It will be continued, and finally we get a recurrence relation. So the energy of nth term, 2n plus 1 h plus omega by 2. So the energy eigenvalues are given as, and its graphical view, and the ground state energy is known as that of 0 point energy. Let us putting that lambda is equal to 2n plus 1, it will be changed to this, that is the Recurrence formula, that is the orthogonality condition, putting y is equal to that much. So using normalized condition equal to 0. Again, so using n is equal to 0, 1, 2, 3 etc., we get the Hormone polynomials as usual, and the eigenfunctions sin x, psi 1 x, psi 2 x, psi 3 x, and its graphical views, and the probability density for that of nth state. This is the probability density, and this is the graphical representation of that of wave function, and this one is the graphical representation of that of probability density term. And finally, the uncertainty relation and linear harmonic oscillator. What is the relation in between these two? We use their consensus manner to derive. Finally, we get that uncertainty in position and momentum, that is the Heisenberg's uncertainty principle, which is related to linear harmonic oscillator and quantum mechanics. So, with this useful and informative notes, let me wind up this session. Thank you.